Okay, so in other words, once we solve for this, then we have some great little psi n's, and I'll go back and use this. It's the same exact formula. What's the only thing that's different?
I don't have a CUM.
Of course we're going to have CNNs.
It's going to,
What's the
that
only
time
difference?
independent part, the G of T.
What's that?
You can figure it out for all time.
Okay, what's the only thing that's different out of all this garbage? Oh, I see what you're saying. CNNs are going to be different, of course. Yeah, okay, I see what you're saying. Has this changed?
No.
No.
Has this changed?
No.
Yes, it has.
Yes.
This
That
is now
changes.
what?
Whatever it is you solve for.
This is now these, the harmonic oscillator. So no longer am I going to be using the infinite well psi n's, right? I've got to use the harmonic oscillator psi n's. That's the only difference. Everybody got it? Okay, when I solve for the hydrogen atom, I'm going to draw a picture, I'm going to write this, and then what am I going to do? Separation of variables, to get a time dependent that will be this, right? And then when I get this, I'm going to solve this, but it's going to be specific for
Hydrogen
the hydrogen atom. Once I get this for the hydrogen atom, what am I going to do?
Put it back up in the original.
Jump up into here.
And get
What's the
the
only thing that's different?
The psi and then.
That's it. You guys got it.
Because you change the psi, then you change the C of that.
Well,
It changes every time. You
See, it just depends upon what it is you started with, you know. But everybody got the picture? See how it's a nice picture of it? I'm trying to...
Yeah, the CNN. It depends what you start with. Just like a four-year analysis is going to be different for
If
whatever
you're thinking
wave.
that, if you're thinking that way, you're great on the money.
Yeah, right.
Yeah, you're doing great. All right. So what we'll do is we'll spend a little bit of time doing these psi n's, little psi's, for all the little different problems. But what do we know when we solve this? So when we solve the shorter time independent one, we know that we can just plug it back into the full machinery of everything that we've just done. How many people are okay with that? Okay, this is kind of a big picture thing. All right.
Just need to do it hundreds of times.
What you do is you solve for the most, cases. Like, there's the infinite well, there's the finite well, there's the harmonic oscillator.
Like you said, you already did that psi-n for that other problem, and then we could go back, and now that we know it, you can just plug that right in and solve for different.
So once you can express that comfort with this, you can go a long way. All right. Okay. So what we're now going to do is we're just going to spend some time solving for some other time-independent problems that we know once we get the answer, you can put it back into that machinery. All right, so let's do it. Let's do the harmonic oscillator. All right, so the harmonic oscillator. Everybody see the big picture? All right, harmonic oscillator. So let's start the harmonic oscillator. And now we're going to just start potential. Okay, let's just start right here. We're going to go H, O, psi, so X equals, and then put in an N. So did I put my psi? Yeah, I put in N. Psi equals E, N, psi. Everybody know why we're starting here?
Because we've already separated the variables.
Yeah, we've already done all that stuff. Okay, and generally speaking, I guess Dale mentioned this, I didn't say this explicitly. When I put the O in there, that's like the basic Hamiltonian. It's the unperturbed Hamiltonian. All right? Not that it's the same Hamiltonian from problem to problem. It's the unperturbed Hamiltonian for each problem. What I mean by unperturbed, it means it's just the kinetic energy and the potential energy for that particular problem.
Yeah, because now you have different potential.
Exactly. So if you're saying, oh, this is all it is, and like Jeremy's saying, you're getting very comfortable with it, and that's very good. All right. So that's right. It's going to be EK. I always start off EK plus EP times psi n, and I'll put that little operator, all right, equals En psi n Okay, now let's get to EK. What's the kinetic energy of this particle trapped in a harmonic oscillator potential? Excuse me?
P squared.
It's,
Or P squared over 2m.
no, that's not the kinetic energy.
Relativistic.
And Schrodinger's is non-relativistic. Wow, you guys think way too hard. All right, but right, Schrodinger's equation is non-relativistic. So what's the kinetic energy? 1/2 mv squared. Right? David said 1/2 kx squared or something like that. Right? You said you put a k in there, and that's not kinetic energy. Okay, so potential energy is 1/2 mv squared. You can write it as p squared over 2m, right?
Yeah.
And I know what the p operator is. It's minus I h bar partial with respect to x. So that thing squared over 2m is minus h bar squared over 2m. And again, it's only a function of one variable, d squared with respect to x squared. So I'm only going to use the total derivative. Is that any different than the kinetic energy we used in the last problems? No. Okay? But, now David, what is the potential energy?
That's the one that kx.
That's the 1/2 kx squared. All times psi n equals En. So, are our psi n's going to be different than the infinite well?
Most definitely.
Yeah, they're definitely going to be different. Okay? So, what we're going to do is, yeah, and again, remember the thing that everybody's emphasizing here is that what's different is just the potential energy part. Is the potential energy term time dependent? No. So if it's not time dependent, then we can use all that machinery. G of t and all that stuff. All right? I'm going to write this a little bit different. So recall our classical harmonic oscillator. We did sum of the forces equals mx double dot. We have minus kx equals mx double dot. We write that as x double dot plus k over m. X equals 0, which we write as x double dot plus omega naught squared x equals 0. Okay, we've done this a million times now. You guys should be able to do this. So omega naught squared equals k over m. So let's see. So we're going to rewrite this a little bit differently. All right, and let's write it like this. We'll say that k equals omega naught squared m. All right, and this is just super clever stuff, okay? So these are just the way to solve this differential equation is just very clever, okay? So we can write this as minus h bar squared over 2m minus h bar squared over 2m d squared with respect to x squared of psi n plus 1/2 omega naught squared m x squared psi n equals En psi n. All right. And let's see. I can write that as, so let's rewrite that as, okay, you ready? It's going to be 1 over 2m p squared plus m omega x squared times psi n equals En psi n. So just make sure that works, all right? And I'm pretty sure it does. So it's p squared over 2m. We just recovered that back, right? And I think this is supposed to be squared. This is sorry, my square should be out here. And if you square that, it's m squared omega squared x squared. But then when you divide by 2m, you get the 1/2 omega squared mx squared.
Right.
Okay? Good. All right, so here's the scoop, is you can solve this, solve diffie-q straightforward way like you do in class. I'll call this the brute force. When you solve this differential equation brute force, do you think you get the answer?
No.
And you do. I was setting you up. You do. But is it hard?
Yes.
Is it messy? Yeah. But is it right? Yeah. So this works. Right? And we'll definitely sketch out that idea. Right? But there's another way. There's another way. Another way. And it's extremely clever, and it's done with ladder operators. Ladder operators. All right, and it's loosely based on the idea. I don't know how far this idea goes, but this is in purpose too. Is that if you have like if you had a squared plus b squared, you could rewrite that as a plus ib times a minus ib. So you could, if you do this out, this comes out to be a squared plus b squared. And so if you look out this thing, it looks like an a squared plus b squared. Okay?
P plus I m omega x
Right.
times a times p minus.
You're getting there, yeah. Okay, so that's loosely what it's based on. So let's try to do this, and this I'm following Griffiths exactly, okay, guys? So this is exactly done in Griffiths. But your motivation is just to get these things. By the way, the conclusion on my sickness is the following. I went to the doctor yesterday. So I have asthma, right? And I've always had asthma, and so I got this cold, and the cold simply is complicating my asthma, and I don't take asthma medicine. And so they yelled at me and said, "You moron, take asthma medicine." And so I'm going to start taking my asthma medicine.
No, don't do it.
Yeah, exactly. Don't do it.
You have asthma
I'm
and
not
you're
on hand, listen.
I've never taken my asthma medicine. I've never had a problem either until I got this cold.
Just throw some more and go running some more.
Yeah, that's what I usually do. Try to get tough. Yeah, exactly.
It's like hack it up.
Yeah, I'll get better.
Right.
All right, and so I have to take my asthma medicine. And what they said now is they said when I have allergies and when the seasons change, I should take my medicine to kind of preempt any problems. And they said if I feel a cold coming on, I should take this medicine to preempt it.
They're working for the pharmaceutical companies. So.
Yeah, they're working for the pharmaceutical. That's all there is. No, but I'll have to go with them on this.
I mean, all these years you're not taking it. It's, asthma. People,
I've never had a problem.
That's kind of funny. And maybe it's just a prolonged sickness. It goes away and you're fine. Why don't you just wait to see?
It kind of just it's a nasty virus. I think people are getting.
Why don't you see it if it goes away, if it never happens again, and it's just some anomaly, instead of like.
They said that I was feeling